Hey guys, it's me Greg, and today's video is an introduction to acids and bases.
So welcome everyone, let's talk about acids and bases and things we already know. So acids release hydride ions into solution, bases release hydroxide ions into solution, and the concentrations of these things can be very, very different from one another. The scale is logarithmic. So the solution of pH 3 has 100 times greater hydride ion concentration than the solution of pH 5. Notice the pH is the negative log of the H plus ion. You'll also notice, if you look at the H plus ion concentration here, that 1.0 by 10 to minus 7 molar is neutral. Presumably that would also give you 1.0 by 10 to minus 7 molar hydroxide ion, so this is not an acidic solution, but a neutral one. And the idea here is that the H plus ion and the hydride ion and the hydroxide ion have this inverse relationship. As one's concentration goes up, the other goes down, and we'll talk about that more later. One of the essential features of being an acid or a base are that they neutralize one another, forming water and a salt. Here we have the reaction between hydrochloric acid, hydrogen chloride dissolved in water, potassium hydroxide forming liquid water and potassium chloride. There's water being formed and the salt, in this case potassium chloride. So a solution that has ions that can move we call electroconductive. More ions with more mobile charge makes the solution more conductive. Distilled water, typically neutral, but it could be an acid or a base depending on circumstances. And what do you mean by depending on circumstances? Well, depending on the context or what other components are in the solution. And when we say act as, that's something we'll need to explore more. Nonmetal oxides tend to make acidic solutions in water. Here's sulfur dioxide bubbled through water, making sulfurous acid. And you can see the sulfurous acid then goes along and dissociates into the hydride ion and the bisulfite ion. This actually happens in an equilibrium, so that arrow there should be a double arrow. We'll talk about acid-base equilibrium very soon. Metal oxides, on the other hand, tend to make basic solutions. Here's sodium oxide dissociating in water, making sodium and oxide ions, and giving you the O2 minus ion. Now that one, of course, reacts with water and gets you a couple of OH minus ions by stealing water's hydride ion. Okay, most acids react with most metals, often releasing hydrogen gas. You can find acids in things like citrus fruit, saliva, stomach acid, and bases in things like wasp stings and blood and so on. Acids tend to be sour, like vinegar and grapefruit, while bases tend to taste bitter. Nowadays, there are far more sour than bitter foods because many toxic things, not all of them, are bitter. Evolution has helped animals, including humans, stay away from bitter foods. Let's talk now about buffer systems, a very brief introduction here to what you may know about them already. This is the body's metabolic processes. They're easily changed by foods that are even the slightest bit acidic or basic. So we need a buffer system to help resist those changes. If not, your body's pH would be altered to the point where a metabolic process could stop entirely. One source suggests 1 glass of orange juice might slow down your metabolism to the point where you could actually lose your life. Concentration and strength are two different things. Concentrated versus dilute, strange but significantly different to strong versus weak. So whether an acid dissociates totally, all the particles dissociate or not, is different to how concentrated those particles are in solution. That's a tongue twister. Okay, so let's talk about strong and weak acids. We just discussed about that. This is a bad phrase, partial dissociation. Collectively, for the whole group, it is possible, such as some particles dissociate and some don't, but one particle either does or doesn't. So an indicator is a large organic molecule, usually a weak acid, and it changes shape when you remove or add a proton. Also, when a proton is removed, bare protons don't really exist in solution. They attach themselves to water, and they form this thing we call the hydronium ion, which is H3O+. So what you have there is you have water floating around in a giant... We have all the water molecules floating around. The hydride ion gets pulled off by a water molecule and sticks to that water molecule in this way, making the hydronium ion. There's a couple of ways to be an acid or a base. The first way, of course, is by what you contain in your compound. So if you have an H plus ion or an OH minus, you're a ion, then you're a base or an acid. Also by what you do. So if, for example, component X, whatever that is, takes a hydride ion from water, leaving hydroxide, X is a base, in the sense that bases accept protons. For example, here's ammonia accepting a proton from water, forming the ammonium ion and hydroxide ion. If X, the compound, takes hydroxide from water, leaving hydride behind, So that component X would be an acid. Okay, so the other thing is talking about sour and bitter. Please don't test acids or bases by being sour or bitter by tasting them. Okay, we don't taste acids and bases to determine what they are. Anyway, that's a fully high-speed review of some of the things we already know in this world here of acids and bases. Really do hope that you'll read a little bit, remind yourself of what's going on there, and look at the next 2 videos for more, and stay tuned for our next lesson in Chemistry 12, lesson number 17.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!